Welcome back once again. Let us do some numericals of chapter 22. The first numerical that we are considering today is the fourth numerical from chapter 22. In this, the air is filled in a bottle at atmospheric pressure and is corked at 35 degrees Celsius. So the initial temperature is given as 35 degrees Celsius, which is equal to 308 Kelvin. If now the pressure changes to 3 atmospheric pressure, then what should be the temperature in order to remove the cork? So using the equation P1 upon T1 equal to P2 upon T2, we get the value of temperature as 924 Kelvin, which is also equal to 651 degrees Celsius. Numerical 7th. Calculate the number of molecules, volume occupied by one molecule, and the distance between two molecules when the volume of gas is 1 centimeter cube at NTP. Now at NTP, the pressure is 1 atmospheric pressure and the temperature is 273 Kelvin. So using the relation PV is equal to NKT, where K is the Boltzmann constant, we can calculate the number of molecules as PV upon KT. Substituting the values, we get the number of molecules as 2.68 into 10 to the power 19. Now volume occupied by one molecule. The volume is 1 centimeter cube, which is 10 to the power minus 6 meter cubes. By the number of molecules that we've got in the first part, the answer is 3.73 into 10 to the power minus 26 meter cube. Now to calculate the distance between two molecules, we'll assume that the molecules are placed in a cubical vessel. Then the mean distance between two molecules is the cube root of the total volume, which is 3.34 into 10 to the power minus 9 meters. Next question is question 15. The volume of a flask is given as 10 to the power minus 3 meter cube, which contains oxygen molecules, and the number of molecules is 3 into 10 to the power 12 at a certain temperature. The mass of one molecule of oxygen is 5.3 into 10 to the power minus 26 kgs, and the root mean square velocity is 400 meters per second. We have to calculate the pressure of oxygen gas in the flask. Now the pressure is given as 1 by 3 rho v square, where rho is the density. So density can be written as mass upon volume. If small m is the mass of one molecule and n is the number of molecules, then the total mass is the product of m and n, and the pressure will be 1 by 3 into 5.3 into 10 to the power minus 26 multiplied by 3 into 10 to the power 12 into 400 square. So the value comes out as 8.48 into 10 to the power minus 6 newtons per meter square. Next is question number 21. Now the root mean square velocity of oxygen at a certain temperature is 150 meters per second, and we have to calculate the root mean square velocity of hydrogen at the same temperature. Now the velocity is given as under root of 3 RT upon m, as T is constant, so the velocity is inversely proportional to the molecular mass of the substance. So the velocity of hydrogen with respect to oxygen will be square root of the molecular mass of oxygen divided by that of hydrogen. The molecular mass of oxygen is 32 and that for hydrogen is 2. Substituting the value of the velocity of oxygen as 150 meters per second, the velocity of hydrogen comes out to be 600 meters per second. Question 27th. The temperature of the gas is 0 degrees Celsius, which is going to be 273 Kelvin. Now we have to find out the temperature to which the gas should to be heated, so that in the first part the average kinetic energy is doubled, and in the second part the root mean square velocity of the molecules is doubled. Now the average kinetic energy of the molecules is given as 3/2 kT, where K is the Boltzmann constant and T is the temperature. Now the kinetic energy is doubled, so let us take E1 as the initial kinetic energy. The new kinetic energy will be 2 times E1. Energy is directly proportional to temperature, so E2 upon E1 will be equal to T2 divided by T1, and therefore the ratio, the value of T2 comes out as 546 Kelvin, which is 273 degrees Celsius. The second part, the RMS velocity is doubled. Now V is equal to under root 3RT upon M. So it's directly proportional to the square root of temperature. So V1 square upon V2 square will be equal to T1 upon T2. The temperature is doubled, so the final temperature is going to be 4 times the initial temperature when the velocity is doubled, which is 1092 Kelvin. And if we subtract 273 from this, we can calculate the answer in degrees Celsius as 819 degrees Celsius. The last is question number 35. The hydrogen molecule in a vessel of volume 200 centimeter cube is given as 6 into 10 to the power 21. The initial temperature is 27 degrees Celsius and the pressure is 10 to the power 5 Newton per meter square. Now the question says that what should be the ratio of the number of molecules, pressure and the average kinetic energy if the temperature is raised to 47 degrees Celsius. Now the first is number of molecules per unit volume. It will remain unchanged. The second part is the change in pressure. Now pressure is directly proportional to temperature. So P1 upon P2 is equal to T1 upon T2. As the temperature, final temperature is 320 and the initial is 300, the ratio of the pressures comes out as 16:15. And the last part is average kinetic energy. So the average kinetic energy is directly proportional to the temperature. Just like the pressures, we can calculate the ratio, which also comes out as 16:15.